Hello everyone, and thank you for coming to my talk. In case you don't know, I'm John DeGoes, and I'm here to talk to you today about some open source work I'm doing on a library that I'm calling ZIO Schema 2. I'm very excited about this library, and I have a confession to make regarding this title here, Euphoric, Codecs, and Dazzling Rainbows. It looks like this is going to be an exciting talk, right? That's why I use that title. Get you in the door, get you trapped, and now I can talk about something that's probably going to be very boring and dry, but useful in the code that you write. At least the pretty colors will distract you. All right, some sort of animation going on here. There. All right. First, I'm going to talk about why I believe ZIO Schema 2 matters. And I do think it matters for a subset of this audience. I'll explain why shortly. And then I'm going to talk about how the original ZIO schema came to exist and some of the problems that it solved. And then I'm going to give you the ugly side of a ZIO schema. So there would not be a ZIO Schema 2 unless mistakes were made. And mistakes were made, trust me. Then I'm going to introduce my new work that I've done with Andre. I'm not going to try to pronounce his last name, but you know the guy if you're in Scala, the guy who wrote the excellent JSONiter Scala library, which is the fastest JSON parser and printer pretty much anywhere. He's working with me on ZIO Schema 2. I'm going to present our work. I'm not going to present the amazing benchmarks that he's worked on, which show you the performance of this new library, but I will talk about those briefly. And then finally, I'll wrap up and summarize the talk and point you in a direction. Okay, why does this matter? Well, I'm going to start with two hypotheses. Number one, most programming these days is handling data. Okay? Some of you buy that. And hypothesis number two, typed programming languages like Scala, as wonderful as they are at handling logic, are actually pretty terrible at handling data. And if you buy both of these hypotheses, then the conclusion is an inevitable consequence of logic, right? Typed programming languages are terrible. And you're like, no, they're not. I'm a fan of static typing. Except you, Dustin. But the rest of us are like, no, you're not. And so you attack the hypotheses, right? Most programming is not handling data. Oh, no, it isn't. Well, let's think about what you do at your day job, right? So you probably don't write Byzantine fault tolerance algorithms, which would be an example of like pure logic, no data, right? Really fun problem, but none of you, I assume, are working on that. Post-quantum cryptography. No, I don't think any of you are working on it. Oh, Ryan comes really, really close to that. So, okay. SAT solving, probably not. Differential privacy? Oh, yes, Ryan, again. Yeah? Someone has an interesting job here. No, these aren't the applications you're working on. Your app looks something like this. You got an HTTP request, and you got to handle it. You got to query the database. You got to make another HTTP request. You got to handle its HTTP response. You got to make another HTTP request. Handle that response. Update the database some more and return some HTTP response. And repeat that times 200. That's modern application development for you. That's the type of work that most of us do, despite the fact that it might not be the most fun thing to do in the world. And this is sort of an illustrated flowchart of what this looks like, where you're decoding the HTTP model into some sort of type structure. You're parsing the JSON, deserializing your domain types from that, doing validation, and then finally, after you do all that stuff, you get to business logic. No, you get to a little snippet of business logic before you have to repeat this process. And that's what it looks like on the other way. It's more of the same stuff. Now, why is this happening? Well, it's happening because we've moved from desktop applications and monoliths to cloud-native development, this cloud-native thing, right? And what cloud-native programming fundamentally does is it says, well, your standard library is no longer the thing that's included with your programming language, but it's all these different cloud APIs and cloud databases and cloud caches and cloud queues and this and that. And so every other line in your program, you're calling some network system, right? You've scattered the logic across hundreds or thousands of these different distributed systems, and you're constantly doing some form of RPC. Data is everywhere. Changing data, deserializing it, serializing it. And so I'm going to say no. I'm going to say that your application, unless you're Ryan back there doing really interesting work, your application is in fact probably just handling a bunch of data. For 95% of the stuff you write is just handling data. But you can still say, no, type languages are not terrible at handling data. No, they're really great at handling data. And, maybe you believe that, but if you've used a dynamic programming language, you probably don't believe that. I'll give you an example of how you can talk to databases without static types in PHP. Here is the one class that you need if you want to talk to a database using PHP. It's a CRUD class. It allows you to create stuff, read it, update, delete it, any table, any fields, getters and setters and all this fun stuff, and you use it like this, and it detects the name of your table from the name of your class. Cool, right? And it lets you do set age, even though it has no idea age exists, and does all of this amazing stuff, and you can update it, you can create it, you can delete by ID, right? This is the only CRUD class you ever need. Just this one. Doesn't matter how many tables you have, you just need this, right? And even though those of us who love static typing know the drawbacks of this style of programming because we've lived them, there is no doubt that you can be extraordinarily productive with a tiny amount of code if you're willing to embrace the full power of dynamic programming. And this is an example where dynamic programming really, really shines. Another example I'll give you is how do you deserialize without static types? We know how we do it with static types. It's not super fun. How do you do it in JavaScript? Res.json. Boom. That's it. It doesn't matter what your data model is. It doesn't matter if it's nested or if it's flat. It doesn't matter what the types are in it. .json is how you deserialize that into something you work natively with in JavaScript. All that boilerplate that you can imagine in a statically typed programming language, gone, out the window. And to make it even more interesting, because schema really is data in JavaScript, here's some code that does a request, gets back the response object, whose fields are all in kebab case, and dynamically changes them all to camel case before then accessing them as native fields in JavaScript camel case. Please show me how to do that in Haskell. If you would, that would be awesome. I'm sure you can do it, but it's not going to be like that. All right, so no, sorry to say, but statically typed programming languages are just not as good at handling data as dynamic programming languages. So then what are we left with? Well, sorry, typed languages are terrible. They are terrible for modern day programming in a certain way, and they're wonderful in many other ways. But in one way that really matters a lot, statically typed programming gets in our way. And so all of this pushback that you see against static types coming from people who love to dive into Python or JavaScript, there's a reason why it's there. There's a reason why the data people and the researchers, they love to play with Python because it's just staying out of their way. And yeah, there's lots of bugs they're embedding into their code that they'll find out later, maybe if they're lucky because of the lack of types, but still, they're productive. These languages stay out of their way. They get stuff done. All right, so the question then is, could we make statically typed programming better at handling data? Could we try to equalize the gap, productivity and joy gap, between dynamic programming and static programming, at least at handling data? And the answer, I think, almost always comes from this concept called reification, which features very prominently in functional programming. What reification is all about is taking a construct in a language like Java that is not first class. It's not a value. You can't store it in data structures, you can't pass it to functions, you can't return it from functions, and turning it into a value by creating a model of it. And all of the really amazing things, not all, but a lot of the really amazing things in functional programming are the result of reification. We took something that wasn't a value, we made it a value, and we gained superpowers as a result. So you take a bunch of statements in a procedural programming language and you turn them into a value, and what do you get? Effects, right? You get effects, and that's where ZIO comes from. It's particularly like, concurrent statements, concurrent async statements. You turn those into values, you get ZIO. You take configuration description, which is, I would describe it as, we want to load this part from here, and that part from here, and this part from here, and we want to change these kebab case into this camel case. All that sort of complicated stuff that you can imagine is part of configuring your application, your big application, in a way that's very robust and flexible. And you turn that information, that description, into a value, which you might call a configuration descriptor. And what do you get? Some library like ZIO config, which has a declarative model of configuration sourcing and transformation and all of that. And you use that. It's very compositional and type safe, and you use that to materialize your configuration from the description. Grammar, so if you're parsing text files or even binary files, anything like that, and you turn grammar into a value, and what do you get? Parser combinators. Invertible parser combinators, actually, because you want to be able to parse, but you also want to be able to pretty print without having to duplicate any information, and that's the idea behind ZIO parsing, which Daniel here wrote. Workflows. So workflows need to run over long periods of time. They need to run reliably. And it's very hard to do that if you don't have a first-class value for a workflow. If you're just writing statements of code, it's very hard to ensure that your code is going to run reliably over long periods of time. How do you solve that? Well, you turn it into a value. And this is just like, I could go on and on and on, right? If you're having pain accessing deeply nested data, how do you solve that? Well, you turn the concept of an accessor into a value through optics. Fields. Fields are, when you turn them into values, become lenses. Cases in an enum or some type become prisms, right? For loops become traversals. So much stuff in functional programming is just taking things that are not values and turning them into values. Now, why does that work? Well, it's because programming languages have so much power. When you have a value, you can do anything you want. You can abstract over it. You can remove duplication, put it in a data structure, pass it to functions, return it from functions, build up little DSLs around that are very custom purpose. You can only do that with values. You can't do that with things that are not values. So that's where FP gets so much of its power. So what we really want to do then is we want to reify structure itself, the structure of a data type. This is a person case class. It's a product type. And what we really want is to turn this into a value, which here I'm going to call a schema of a person. And inside the schema of a person, we want data. We want to be able to look in here and say, okay, well, this schema is actually a product type. It's a two-way product type, and it has two fields, and the name of the first field is name, and the name of the second field is age, and the type of the first one is string, and the type of the second one is in. So we want there to be data inside this reified structure. But also, we want there to be capabilities. We want there to be an ability to construct a person from its foundational ingredients and to destruct a person down to its ingredients. You want to build it up and tear it down. And that is essentially all the same information that your compiler has access to at compile time. Right? When you're compiling this, your compiler knows that it's a product type. It knows what the field names are. It knows what the types are. It knows what the constructor is, what the deconstructor is, so it can do pattern matching. It knows all that. But once you turn that into a value and make it accessible to your program, so you can do cool stuff with it, it becomes something like this schema here. So one of the first attempts at doing this in the Scala ecosystem was done by a Scala developer. I think he's moved to Rust these days, like many of us, but a Scala developer by the name of Chris Nuttycombe, and he came out with this interesting library called Xenomorph that turns schemas into values. And I was really interested in this library. It didn't really go anywhere, and it used shapeless, and it took a long time to compile. Shapeless is a type-level library that you never want to introduce into your Scala program because of how slow it is. That was its reputation back in the day, and relatively difficult to use. So I looked at this, and I was interested, but at the same time, it's not exactly what I wanted. And between jobs, I took some time off, and I ran this mentorship program. And I mentored about 300 people, so I called it the Spartan program. And it was a crazy thing to do, but I had a lot of fun, and I made a lot of connections. And we worked on open source. And so I was thinking, at the time, we need to tackle this problem. And so a contributor by the name of Valentin Kazas, a very talented Scala developer, stepped up, and he built this library called Scala Z Schema, I think, but the shorthand informal way to refer to that was just Schema Z. And Schema Z also turned schema into a value. But the bad thing about Schema Z is that not only was it unfinished, like many of these attempts, but you had to have a PhD in category theory to use it. Like many things, right? And it's beautiful. It's beautiful. Fixed point data. Right, recursion schemes, hylomorphisms, isomorphisms, great stuff if you know all of it. So there's just not many people who can work with a library like this. So I went back to the drawing board and I worked with some other contributors, and I just came up with something very simple. And it was this data type here that says, well, every schema is either a record, sequence, enumeration, transform, primitive, tuple, or optional. And it started like this. This was the birth of ZIO Schema. And it looks simple here. Wait till you see what it became. Just wait. This was not complete, by the way. You actually can't do too much stuff with this, but it's like in the direction. So way too many commits later, and who knows how many release candidates, ZIO Schema 1.0 came out. And it actually turned out pretty great. So you have your own data type there, like person, and you can have the compiler through macros basically look at the structure of that at compile time and pack all of that information and all those capabilities into a schema data type. So now you know that it has these fields, they have these types, you can tear it down and you can build it back up again. And what do you get from schema? Well, what do you not get from schema? So really a testament, I think, to this data structure, despite how complex it has become, is you get a lot of free stuff out of this. An example is you want Protobuf, serialization, deserialization, type safe validated with error messages, one line of code. This is something you can do, you would take for granted in a language with dynamic types, but we don't have to take that, we can't take that for granted in a language with static types. Here you get the static type safety, but you also get your push button Protobuf. And not just Protobuf, but JSON, message pack, Avro, Thrift, BSON, all of these things are implemented, tested, they work. Push your buttons and get whatever you want. Right? Your data types in any kind of format you want, suitable for interchange, for RPC, for long-term archiving, serialization, whatever you want, it's there, out of the box. Default values. So I don't know if you like default values, but there's this wonderful type class in Haskell that no one admits they use called default, which can summon a value of any type out of thin air. The idea, it turns out to be somewhat handy from time to time. You get ordering out of this, right? If you know the structure of something, you can provide a total ordering on values of that type. That's very reasonable without you having to implement it. Of course, you can do equality, but here's one of the cool things. You can do diffing, arbitrary diffing on algebraic data types. Any two algebraic data types. Doesn't matter what sort of structure this type has, you can diff any two values of that type. And you get back something that's a patch, and you apply the patch to the old one to get the new one. So it satisfies all these nice algebraic laws and has a lot of applications in like event sourcing. Basically, a patch is an event. An event of some, all events are patches, and that's the right way to think about events, is it's a patch on the state of a system. And you have the ability to do not just the diffing, which you can actually see, you can render that if you want, but then that patch structure, which can be serialized, can be stored, and so you can process it like an event. Validation is another thing you get out of this. You can define validator as pure data, and then you can apply it to your data types. You can take this validation and you can send it across a wire, right? Your code can accept arbitrary validations. You don't even know what they are, and you can apply them to this domain object that you might not even know what is. So it opens up the door to do generic programming in a way that, again, you take for granted when you're doing dynamic programming, but it's just not easy to do when you have static types. And then for the ultimate in power, when static types completely and utterly fail you, you just take your statically typed value, you convert it to something called a dynamic value, which is basically a superset of JSON. And in that semi-structured form, you can do anything. You can rename fields. You can anonymize data, right? You can go out to the leaves and you can anonymize data, any sensitive information. You can do all this generic stuff across any data structure whatsoever. And if you don't screw up the data too bad, you can even go back to the world of types. And if you did change the structure of it in an incompatible way, then you get back the error message. So this allows you to drop down in a statically typed programming language into the world of dynamic types where all things become possible. And then one of the applications that the original version didn't have, but I added at some point, was the ability to generate accessors for fields of a record. And these accessors are pure data. And so you can use them in DSLs. And even though an end user of ZIO Schema would never use this, but nonetheless, several library authors use this to great effect. So ZIO DynamoDB has this syntax that lets you do like, select all person where person.age is greater than 20 from DynamoDB. How does that work? Well, person.age is an accessor that's actually generated by ZIO Schema. And it's pure data, so it can be converted to the thing that DynamoDB needs in order to allow you to do a filter on your query, on your scan over your DynamoDB table. It's also used by ZIO Elasticsearch. It was used by ZIO SQL. It's used by a number of other libraries. So there are some major drawbacks to the way it's done. But nonetheless, this proved to be popular for library authors because it allowed them to have these DSLs that are very nice and typed without having to implement any macros or any of the hard stuff that is baked into ZIO Schema. All right, so problem solved, at least somewhat, right? Type languages can be awesome. It can be pretty awesome. If you have a library like this that allows you to turn schema into a value, was there question, problem? Oh, okay. Turn schema into a type value that has all these powers, then you can actually equalize the difference in power between dynamic and static type programming languages. You can have your cake and eat it too. All right, well, it's not all glamorous. It looks all glamorous from here, but I know how the sausage is made. Yes. Sorry, Dijkstra, but I made some mistakes along the way. One of them was, dang, it's a lot of work to build a codec. A lot of work. And part of the reason is every time you build a codec, you need to do a pattern match on schema. And schema is a 65-term sum type. I couldn't fit all that on this slide. So you only get the first, 10, 15 lines. There's another like 50 lines of code beyond there. That's not fun. So adding a new codec, we have actually quite a number of codecs, but it's not a very simple thing to add a new codec because of all this pattern matching. Also, in any library like ZIO Schema, you're faced with the task of abstracting over construction and deconstruction, right? And abstraction is about forgetting the differences and retaining the similarities. So you need to be able to describe all possible constructions and deconstructions in a uniform way. How do you do that? Well, tuples, right? Because tuples have different arity, but you can use them as input to a function. And so you can say that case class 1, you just pass a single value. Case class 2, you pass a tuple 2. Case class 3, pass a tuple 3, and so forth. And so you end up building this system that actually has runtime overhead caused by the abstraction. The runtime overhead derives from two different ways. Number one, all of the inputs to a constructor are boxed in tuples. Number two, if some of those inputs are primitives, they are boxed into on-heap structures. Java lang integer, Java lang float, Java lang double, etc. So you've got boxing of primitives, and then you've got boxing of all of the inputs to a constructor. And then there's various other types of boxings here, but all of this interferes with performance. Then, probably after the first release, we realized that some people wanted to be able to take these schemas and serialize them, send them over the wire. Makes sense, right? Sometimes you just want like a schema registry or something like that. You might want to do some validations or know about the structure of some data that you're responsible for validating or serializing. So you want to take this schema and you want to send it over the wire. There's a big problem though with ZIO Schema. ZIO Schema stores Scala functions. I don't know if you paid attention to that ADT, but like there's transform here, which is actually storing functions. So ZIO Schema is not pure data. It's data plus functions. And whenever you have data plus functions, then unless you're in unison, you can't just send that over the wire. So we had to invent something called metaschema and had all these hacks and nonsense and replication. And this is a big ball of spaghetti that I don't ever want to go back to. Just a big mess. And then I went a little overboard with the type level stuff, as we often do. I should have learned my lesson. The previous 98 times I did this, I was trying to help, honestly. I was working with a contributor in ZIO SQL, and I'm not scared of type level programming. I quite enjoy it. It's like Sudoku or something like that. And you know where Sudoku-driven development leads, right? It leads to something like that. And so you've got all these types, and you've got a massive amount of complexity. And here's my philosophy. Type level programming, it can be helpful in the early stages to get just a little tiny bit of type safety. But whenever you have to work even a little bit, then you should just abandon it and accept whatever unsafety arises at runtime, which you can protect using things like option and either and whatnot. It's just not worth it in most cases. It's just not. So my current philosophy is if I ever have to write something like this, I know I've headed down a path and I back up and I'm like, no, we're not going to go there. Not again. And then another thing that I'm not, some people have no problem with annotations, but I am not happy with annotations. I really hate annotations. And ZIO Schema came to rely on annotations. And annotations are extremely addictive, right? Like crack. And you try the first one, the second, and then before you know it, you've got 20 annotations, you're in Springland. And the problem with annotations is, in some sense, like all these like overrides are duplicating information that's in the schema. Like here we have one called a field name. right? So there's a field name in the schema, and then there's a field name attached to the structures and annotation. And if you're writing a codec, you have to look at the schema and say, oh no, we're going to ignore this one. We're actually going to pay attention to the annotation that's attached to the class. And also, why have two different ways of doing the same thing? There are reasons for these, right? Because the other way of doing this is so nasty and awful that you would never ever do that. Right? If you didn't have these annotations in ZIO Schema 1, people would be not using the library. So it's a compromise. It's a yes, you want your addictive candy, well, here it is. We're not too happy about it, but we're going to give it to you because we want people to use this library. And then, not in ZIO Schema proper, but in some of the different codecs that we support, configuration is threaded through using implicits. Implicits created all sorts of, basically, it's the compiler auto-magically passing parameters for you in certain cases. Created so many problems in the Scala community, pushed so many people away from Scala. Implicit abuse was a thing that in Scala 3, Martin had to rename implicits to givens just to get people to program in Scala 3. But they're still there doing their evil work. There's very useful ways to use givens or implicits, right? There's definitely legitimate ways. I'm not convinced, however, that altering the runtime derivation of custom type class instances, such as JSON codec, using implicit configuration is a good use of implicits. All right, I'm going to scroll through schema here to give you a sense for what these 65 terms of this monstrous sum type look like. This is one file. It's a single data type. 65 terms in this ADT. Don't worry, we're almost to the end. Yeah. A nice little coffee break. Okay. There. Yes, it was before the days of Copilot. All right, so if we attempt to go back and fix any of these problems, we run into that. I don't want to fix any of those problems because I don't want to edit a 10,000 line of code file and update all the dependencies that are using that file and relying on its structure and its type numbers and its fields and everything else. All right, well, what to do? What to do about that? Well, you know what we do, right? We just rip it out, replace it, we rewrite it. And why it's more fun than working with the old stuff, and that's what I did in ZIO Schema 2. So ZIO Schema 2 is basically a clean slate implementation of reified schema, which I hope learns from and improves on its predecessor in every possible way. And also, interestingly, it has zero dependencies. That means you can use ZIO Schema in any Scala ecosystem. And I think this is a big thing in Scala, just more libraries having fewer dependencies, because the whole community is smaller. It's a lot smaller these days. And you can't afford, as fun as it is, you can't afford 98 versions of JSON library anymore. In the old days of Scala, when we had so many people working on it, we could. But in the new days, you know, probably 12 JSON libraries is enough. And hopefully one schema library will be enough. So what does it look like? Well, the basics are pretty much the same. Schema is a case class that stores a single thing called reflect. And reflect is a reflective data structure I'll talk about more in a second. And you derive it in a similar way, or you can use Scala 3 deriving syntax. So at a high level, if you're a user, it looks pretty much the same, right? And is going to have pretty much, when it's all done, it'll have pretty much the same methods on the schema data type that you have on the current one. Not all of them, there's not going to be transform, for example, but it has a lot of the same stuff. And here's what the underlying ADT looks like for reflect. Instead of 65 terms, you have 7. Beautiful. Record, right? That's product type. Variant is your sum type. A sequence can handle all the different types of collections. A map, of course, is important, an important difference from a sequence. Primitive does things like strings in state times and all that stuff. Dynamic is actually, it's for things whose type you don't know. And that turns out to be very important because lots of times you have payloads that are JSON or whatever, you need to be able to model them. And so that's dynamic value, basically. And ZIO Schema's way of thinking about that, we had that in the previous version. It worked out very well. And then deferred is just introduce laziness, so you can have cycles because you want to do things like recursive data types, recursive ADTs, or mutual or recursive ADTs. And so you need some laziness in there to be able to tie the knots. One of the key innovations is box-free construction and deconstruction. So unlike the predecessor, there are no tuples here, none whatsoever. No tuples and no boxing of primitives. Not even any allocation, right? So 0 allocation, 0 boxing, construction and deconstruction of records. It doesn't get faster than this. You can't make generic code in Scala faster than what's been done here. And how this works is it uses this data structure called registers, which has a byte array that's used for storing intermediate primitives like ints and other types of things that you would ordinarily have to box. And then it has another array of basically pointers, any ref, for storing pointers to on-heap structures, objects. And if you reuse registers, then without any allocation, you can construct and destruct things all day long. Now, to actually deserialize stuff, you will be obviously allocating on the heap because you're going to return an object that's on the heap. But the library itself is not adding any overhead by its attempt to abstract over construction and deconstruction. And that's big and allows us to achieve performance numbers way in excess of its predecessor. In addition, in order to express derivation of a codec, it is only necessary to implement, I'm going to simplify this rate. There's still some stuff here I'm not super happy about. I'll simplify it before I ship it. But you only need to implement this trait, and it's 1, 2, 3, 4, 5, 6 methods. So if you can implement 6 methods for something like JSON codec or Avro codec or eq type class or hash type class or whatever, then boom, you have yourself derivation for anything that can have a schema. And this derivation is very smart, and it allows overrides of certain parts of the structure. So if you need custom type class instance for one part of your data type, you can achieve that using this without having to solve that in your own code. Your own code is just dumb and does the derivation in the dumb way by implementing these 6 methods. But you still don't lose any expressive power or configurability. Here's how this looks like. You have some type class called JSON codec, for example, which has 2 methods, encode and decode. And then you extend deriver of JSON codec. You implement your 6 methods. And now if you have a schema in your hand, you just call .derive, and you pass that deriver. And it will go ahead and derive that structure based on everything. And even has smart caching. So if you're deriving this at multiple places in your code base, you're only actually doing the work one time. It also has, how we solve the sort of schema, meta-schema problem is this reflect structure, which is embedded in schema, has this pluggable data type. And it's called F. Like it often is in Scala for Haskell reasons, it's called F. And you can plug in a binding in here, in which case the nodes of your ADT have capabilities inside them which allow you to break them down into simpler parts and rebuild them into the original structure. So for example, there's a binding for records, there's a binding for variants, there's a binding for sequences, there's a binding for maps, there's a binding for primitives, There's bindings for all those things that let you do construction and deconstruction. However, those are going to embed code inside the schema data structure and make the resulting schema not serializable. So you can also plug into F, you can plug in no binding at all, which is no functions. You still have the structure and the types and the names and all this stuff, but you don't have the Scala functions. And those can be serialized across the wire without the need for a parallel type hierarchy called metaschema. You can also think to yourself and create your own bindings, right? If you're building some DSL for DynamoDB or a different programming language or whatever, you can create your own bindings and you can plug that in there. So this is actually used by the deriving machinery, right? Because it's storing type class instances inside there as it's doing the deriving. You don't see that, but that's what's actually happening, is it's plugging its own binding into that. So it's very handy and configurable, and as a user, you shouldn't need to deal with this. This is only going to affect library authors who are building extensions for ZIO Schema. All right, and now we come to the highlight of ZIO Schema 2, which is something I'm very excited about, something called reflective optics. And before I can tell you what reflective optics are, I have to do a little primer for those of you who don't know what an optic is. Optics are reified fields and cases and for loops. What they allow you to do in a functional world is drill down into some deeply nested data structure and either look at a value and pull it out, or change the value and get a new top-level structure. Why a new one? Well, because in Scala and FP languages, everything is immutable, so you don't change existing things. You just copy them with modifications, patches applied. So optics allow you to, in a very easy compositional fashion, like zoom into the age of a person and change it or get back a new person. And these optics here have two type parameters, source structure and the focus structure, and you can think of them as like the big thing and the little thing that you're focusing in on. And that's where the terminology optic comes from. It's like a little magnifying glass and you're focusing in on this piece. And all the terminology, prism, it all comes from optics. This is what a very simple optic looks like, called a lens, which is designed to allow you to access a field inside of a case class or a term inside a product. What is a lens? It's basically a pair of functions, a getter and a setter. It's a reified field. It allows you to get and set generically. And the cool thing about a value like this is I can now pass along the ability, as a value, pass along the ability to get and set to generic code that doesn't know anything about my data structure. And it can now get and set stuff that's deeply nested in it. Super cool, right? It goes beyond what you can do in most programming languages that have great support for getters and setters and Elvis operators, their own versions of copy. And in the case of Scala, you can't do any of that with those language-specific mechanisms. They're very easy to do with optics. Optics, however, achieve their greatest power from composition. So if you have an optic over here and another one over here, you can compose them together and get an optic that allows you to zoom in on something that you're already zoomed into and modify the inner thing. And that's what that looks like if address has a postal code, so you have a lens for that, and if person has an address, you can compose those together and get an optic that allows you to zoom all the way into the postal code, which is inside the address, which is inside the person. This is a simple one-slide model for the common optics. Got lens, prism, traversal, optional. Lens is fields in records. Prism is cases in enums or variants. Traversal is elements in collections, and optional is combinations of lenses and prism, basically. All right, so reflective optic. What does a reflective optic do that an ordinary optic doesn't? Well, take a look at all these optics. These optics are defined by functions. Functions give us capabilities. Functions are code, and they give us capabilities. So these optics gives us the ability to get stuff and to change stuff. A reflective optic goes beyond just allowing you to get stuff and change stuff, and actually incorporates data into the structure of the optic. What does that look like? Well, in ZIO Schema 2 terminology, every optic, it still has like the source and the focus, but the optic itself embeds the structure of the source as a first-class reified schema, as well as the structure of the focus. So this means you can peer into the source and you can say, wow, okay, this lens is allowing me to access this structure, and you have the type IDs, you have all the fields, you have that all the way down to the leaves. And then you can look into the focus and say, okay, well, I'm accessing this, I know what its shape is, it's a variant, etc. And so in a way, reflective optics combine the code or capabilities of legacy optics with the data of typed schema, giving us something that optics have never had before, which is the ability to do arbitrary introspection on the structure of the terms that you're accessing through these optics. And let me show you just a few pretty cool things that you can do with this capability, one of which is amazing error messages. Optics don't have error messages. If you've ever used a standard optic library, you go to update something, you've got this chain of 20 composed optics, and you get back the same structure you started with, or maybe you get back a none. You're like, what? I wasn't expecting that. I wanted to do an update. What went wrong? Well, it could be you attempted to access the left side of an either when the value was actually a right. It could be you attempted to modify an element in a collection, but the collection was empty, right? So many possible ways things can go wrong when you're using optics. And sometimes those are not error conditions, so don't get me wrong there. Sometimes you don't care. But sometimes you do care. And when you do care, finding out which thing was a none when you needed it to be a sum is an exercise in print line, our good old friend. With reflective optics, you can instantly, at any time, get back the error message during attempted access at .addresses, .each, .state or province, .when Colorado encountered an empty sequence at .addresses. Why did this update fail? It's because address is empty. Error messages in optics has been so problematic. I know Ed Kmet, as well as other people, have worked on error reporting optics, trying to get info. They've all been abandoned I don't think anyone uses them because they have their own drawbacks. They're not as compositional. But nonetheless, it is a pain point, and it is a pain point exceptionally well solved by reflective optics. Another amazing thing here is that instead of having a separate mechanism called like accessors and having to use accessor builders and all this type level stuff that we used in the previous ZIO schema, these optics are actually, because they have the structure and data embedded inside them, you can natively use them in DSLs. You don't have to do anything. You can actually, a SQL DSL, for example, can reach into the user.name optic, and it can know that it's accessing a user structure from which it knows the table, and that it's accessing a field called name inside that user structure, and it knows the string, double quote name. So it can look up the column. And that's amazing. It means that in your application code base, you only need a single set of optics to allow you to access and modify your own data structures, as well as to be able to use those data structures with DynamoDB and Elasticsearch and relational databases and anything else out there that you want. One optics. Not the current ZIO schema way of thinking about this, which is you need monocle or quick lens, and then also for ZIO DynamoDB, you need your own accessors, and then for Elasticsearch, you need your own accessors. No, one optics to rule them all. And these things are so fast, by the way, that there's no reason that you need monocle or quick lens anymore, right? The performance already, we have more to go to optimize, but already these things are so fast on your own data structures, there's zero reason to use a third-party optics library. one of the really cool things that you can do with these reflective optics is you can allow people to zoom into parts of a structure and augment it or enrich it or override it in some way. And I use this feature to allow you to specify custom type class instances when you're deriving. This is all value level machinery. We zoom in to person.age here and we say, for this specific part of this nested data structure, we want to use our custom age codec. And you can do that as deeply nested as you want. You can specify that declaratively. It's all a value. There's no need to use any implicit machinery. There's no need to wonder about which implicit Scala is going to pick in this case. You can be extremely explicit about this. And you can also change your mind, right? This part of the code wants to use this custom instance for age, but this other part of the code wants to use this other instance for something else. All of that works and allows you unprecedented degree of expressivity. In addition, this allows you to zoom into parts of your schema and apply custom changes. So for example, you can zoom into person age, add some documentation. Zoom into another structure and add validation. Zoom into another one and specify the casing here for the field name should be kebab casing. All right, all of this power in a compact way at the level of values and not non-values like annotations. This is the ticket to eliminating annotations. I'm not saying we won't support annotations. People like their candy, but I think we can make it so that it's actually pretty fun and pretty cool and pretty powerful and flexible to use this instead of having to annotate stuff in all your case classes and sealed traits, etc. Patches. Kudos to Adam here for the idea. This is an early stage implementation of the idea of allowing you to create these patches which are 100% data. And they're basically pairs of optics which can be serialized as well as an operation on that value. So super compact encoding of changes that you can then serialize, deserialize. And this is going to be the key to enabling lots of event-driven architecture, event sourcing, CQRS, all kinds of crazy stuff. It's going to be very easy to do without you having to think in terms of events, right? When you're thinking in terms of events, you're not thinking in terms of patches, but this will allow you to think at a higher, more algebraic level. I want to patch this state explicitly, right? And then serialize that. I don't care what the structure is. On the other end, I'm going to deserialize that and apply that to the objects whose state I'm trying to change. There's also a really cool thing you can do here, which I use internally in the library, but I'm exposing this thing called schema metadata that basically allows you to take and augment a data structure with custom information. So you would use this a lot in compilers, right? Because compilers have all these phases, and in different phases you want to attach like a type to this part of your tree, and you want to attach something else to this part of the tree, etc. And it's hard to do that. And doing it in a generic way, typically you have to go and modify your data structure if you want to be able to add new stuff, right? But with these reified optics, reflective optics, you don't need to do that anymore. You can actually store arbitrary information on a tree-like value outside the tree and retrieve it and set it in a type-safe way and even fold over it in a type-safe way. So this allows you to augment data structures you don't control, like with timing information or logs or auditing lineage or whatever you want. You can start to program with data itself in a generic way, which is not something that statically typed programming languages can do generally. In the world of JSON and JavaScript, right, you just add your dot properties and add whatever you want. You can do that easily, but here we're equalizing. Oh, yes, they're going to kick me out. 5 minutes to lunch. Okay, yeah. You weren't hungry anyway. No, I'm almost over. I am. I'm making good progress. And then this other thing, which I haven't implemented, I'll probably implement tomorrow, actually, that I think is super cool, is aspects. Aspects appear pervasively in the ZIO ecosystem, and what they are is transformers. So if you were at Daniel's talk earlier, you saw an example of a ZIO test aspect, which transforms a test. And these things that I'm calling schema aspects will allow you to transform schema. And so you'll be able to say, here's my schema, and I want to apply all these different aspects to different parts of my schema. And you can see here how power is unlimited. It's unlimited. The amount of stuff you can do here in a compact fashion. And because it's all values, you can extract out duplication, you can put out common stuff in functions. It gives you the best of all possible worlds. Here I'm attaching default value to person addresses. I'm adding some verification to age, saying it has to be between 0 and 100. And I'm saying that the addresses field is going to be, or maybe everything inside it is going to be kebab case. A type registry is something we had a lot of calls to do in ZIO Schema 1 that I am doing in ZIO Schema 2. And a type registry lets you say, okay, for this data type here, I want you to use this binding. And where this is useful is sometimes you want to serialize a schema, and then on the other side of that, when you deserialize it, you want to be able to reestablish bindings using a registry, which allows you to construct values you don't even know what they are, right? So you have some catalog of X number of types in your application that you deem safe to allow constructing in arbitrary compositions. And you deserialize this schema, and then now you're able to make values of that type, parse values of that type, all in a way where you're actually using your Scala data structures. So very frequently requested feature of ZIO Schema. I could never do it in a way that made me very happy in ZIO Schema 1, but I can do it in a very nice way in ZIO Schema 2, and I will. And this is an interesting idea. I don't know if I'll do anything with this one, but it's just very curious that when you have these reflective optics, you don't actually need any values of the source structure types to exist in memory. You can totally virtualize data. Ordinarily, like physical data, like when you have a case class value in your hand, you're actually combining two things into one. You're combining data representation, the representation of your data in memory, as well as where it is, it's local. You're combining that with the ability to modify and access the data. You're really tangling those two things into one. And it makes sense, right? Because if you have the representation in memory, then obviously you have the ability to change those bits. So that's an embedded capability of it being local. But what reflective optics allow you to do is take these two bundle of things and peel them apart and say, okay, well, we can independently choose what our data representation and locality is. Maybe it's Java's way of laying stuff out in memory, but maybe we're using off-heap storage. Maybe we're using compressed storage. If we're working in analytics, maybe we've got columnar compression, right? To be able to hold a huge amount of things in memory at once. Maybe we do columnar compression, and that's our in-memory representation. Or maybe it's not even local. Maybe it's remote. Maybe it's on a different machine. Maybe it's not even stored explicitly. Maybe it's a bunch of patches, right, over a data structure, which is one I mocked up here. And then we can separate the sort of choice of representation and where it is, whether it's local or remote, from how we access and modify that. And you don't need to know. That virtual thing, virtual person there, where does that exist? You don't know where it exists. It could exist anywhere or not exist. That could be implicitly a fold over a bunch of patches. You would never even know. Because you can get it, you can set it, you can do all these things with it, which opens up the door to some very interesting applications. Like durable objects, for example, could be powered by this feature. All right, so what's left to do? Well, I've got to implement type registry, continue with the patches stuff, and do the schema aspects, which I'm really excited about. But also I need to polish up the existing support for Codecs and have some worked examples there to fully flesh out any edge cases and rough corners. The existing Codecs will need to be ported to the new one, because we don't want to lose Avro and JSON and all these other codecs. They're great codecs. We want to get them all in the new one. I want to continue simplifying and generalizing this because I know some parts of it look a little rough right now, and I know I can sacrifice maybe some generality, or in some cases, like further abstract in order to get this thing down to its essence. It's pretty close. It's like within a stone's throw, but I think that I can do better on that. And then reflective optics in particular, they just open up new ways of thinking about things. Like right now, every reflect node stores documentation. That's not actually necessary. With reflective optics, you could store that outside the reflect nodes. Right? So there's a lot of things that have to be thought through. With this new capability, with this new superpower, do we really want to make this a more straightforward port of the old one, or do we want to really change things up and see if we can aim for something that's much simpler and much more orthogonal? So I think there'll be a few things that end up getting resettled after I have a chance to fully process the implications of this. All right, conclusions. Well, type languages just are not great at handling data. And we can actually equalize the power to a very great degree by reifying structure as a first-class value. And ZIO Schema is taking that idea, which originated in actually before ZIO Schema, all the way back to Xenomorph, but which was first sort of productized in ZIO Schema 1, and it's making it even better. And reflective optics in particular is something I'm extraordinarily excited about because I think that it has the ability to escape schema and codecs and enable you to do things in your application programming that you couldn't do before, but we'll see. Look for an RC soon. Actually, look for like 23 RCs or however many it takes until the library is ready. How can you help? Well, you can contribute right there. In fact, you're going to have an opportunity to contribute at the ZIO Hackathon tomorrow. We're going to have lots of cool prizes, and I'm going to focus the contributions on ZIO Schema 2. So if you want some fun stuff to do in ZIO Schema 2, come and work on that hackathon. But I should also say there's another hackathon that I want you to go to, which is the Golem hackathon. And you should probably do both. Plan on doing both.
Are they not simultaneously?
They are, yes. So, but you have 2 eyes and 2 hands for a reason. You have a phone. You have phone, laptop. Make it work. Port this to other languages. Right? This is really cool stuff, and ZIO's been ported to a lot of different languages. ZIO Schema, I think, has already been ported to TypeScript. They have their own version called Effect Schema, and it's really great. But this type of stuff, I think, can be ported to more languages. Just please don't port it to Rust, because I want to do that myself. Give me 3 months, okay? If I haven't done anything in 3 months, then okay, port it to Rust. All right, well, I'm very excited about ZIO Schema 2. I hope you check it out. Give me feedback. Contribute to it. I'd love to hear your thoughts.